Physics part 345. F is equal to BQV sine theta. And so we conclude the summary of the section by the last point. The path of a charged particle moving at a constant speed in a plane at right angles to a uniform magnetic field is circular. And now we've got few section questions, and we will be followed by those examination questions as well. But right now we've got few section questions. Well, number one, a stiff straight wire has a mass per unit length of 40 gram per meter. The wire is laid on a horizontal bench and a student passes a current through it to try to make it lift off the bench. The horizontal component of the Earth's magnetic field is 18 U Tesla in direction from south to north, and acceleration of the free fall is 10 meter per second. State the direction in which the wire should be laid on the bench. Calculate the minimum current required. Suggest whether the student is likely to be successful with his experiment. Question number 2. The magnetic flux density of B at a distance r from a long straight wire carrying a current is given by the expression B is equal to 2.0 into 10 to the power raised to minus 7 into I over R, where R is in meters and L and I is in amperes. Calculate the magnetic flux density at a point distance 2.0 centimeter from a wire carrying a current of 15 amperes. The force per unit length on a second wire also carrying a current of 15 ampere, which is parallel to and 2 centimeter from the first wire. Suggest why the force between two wires is demonstrated in the laboratory using aluminium foil rather than copper wires. Question number 3. A small horseshoe magnet is placed on a balance and a stiff wire is clamped in the space between its poles. The length of the wire between the poles is 5.0 centimeter. When a current of 3.5 amperes is passed through the wire, the reading on the balance increases 0.027 newtons. Calculate the magnetic flux density between the poles of the magnet. State 3 assumptions which you have made in your calculation. Question number 4. The figure shows the track of a particle in a bubble chamber as it passes through a thin sheet of metal foil. A uniform magnetic field was applied into the plane of paper. State with a reason in which direction the particle was moving. State with a reason whether the particle is positively or negatively charged. Electromagnetic induction. This is our yet another section in the same chapter, and by the end of this section you should be able to define magnetic flux and the Weber. You should be able to recall and solve problems of using sine to BA. You should be able to define magnetic flux linkage. Infer from appropriate experiments on electromagnetic induction that a changing magnetic flux can induce an EMF in a circuit, that the direction of the induced EMF opposes the change producing it. The factors affecting the magnitude of the induced EMF.